So, to begin, we'll be going over homework one, part B, part one. So we'll be going over how to derive our P bubble temperature, our P bubble, our pressure at bubble temperature, our pressure at dew point, our temperature at dew point, and our temperature at bubble point, and we'll derive these equations. So we'll start out by talking about the LVE diagram that we're trying to make. So right here, we have a pressure and our XY dependent graph with temperature constant. And so this right here is liquid at this high of a pressure. And once you drop the pressure, you start to get into the vapor phase. So let's say you start here and you drop the pressure down. At this line right here, you're going to hit what's called the bubble point. And so that's basically where the first bubble starts to form, and we know our liquid molar percentages here. And then on the other side, if you have a very low pressure and you raise it up, eventually you'll reach this line, and this is what's known as the dew point line, which is where like the first drop of liquid forms. And before that, when you reach here, you assume that the concentration is the same, so you know your liquid mole fractions, so or your vapor mole fractions. So and we also assume that this acts in ideal gas law, so we can use Raoult's law to get our equations. So Raoult's law is Y1 or I is times the total pressure is equal to XI times PI sat. So this is Raoult's law right here. And P sat is dependent on T. So this is Raoult's law, and so we can kind of manipulate this to get the 4 equations that we're planning on getting. So the first equation I'll go over is our P bubble. So we know that Yi, or if we divide P over R, and P is our total pressure of our system, divide P over, we get equal to XI PI sat T divided by P, and then we take the summation. We know that the summation of Yi will total or sum to 1. So this is going to equal 1. So 1 will be right here, and we have the summation of XI, and this is our, and this P right here is our, we call it our P bubble when we're trying to manipulate for this equation. So XI P sat, and then you times the P bubble over, so we can go ahead and erase this. You times the P bubble back over, and you get P bubble is equal to the summation of our XI P sat as a function of time. Okay, so this is our P bubble temperature. Pretty easy. So next thing we'll look at is our P dew point temperature, and this works basically the same way, except that this time we know our liquid molar fractions, or molar fractions. So we'll do the opposite this time, and we'll do Yi equals P dew over, because we'll divide P saturated over, which I'll just write it out just to make it look clear. So it's equal to P sat of T XI divide P sat T P sat T, should be a capital C. Okay, and then so we have Y, I, and then we have our P dew, and over our P I sat of T is equal to xi. So then again, we take the summation of both sides, and we know that xi at this point, at the dew point, the molar fractions are gonna add up to 1 again. And then we know that, so now that we know that that is 1, we can times, I'll just do the algebra. So we have our summation of yi p dew over pi sat t. Okay, so then we have our 1 right here. So we're gonna divide by we're gonna get our yi and p sat over to the right side. So we're gonna end up with 1 over our yi pi sat t with our summation right here. So to write this down a little bit better, get it in terms of p dew is equal to our 1 over our summation of yi over pi sat t. And this is our p dew equation. So we have our two pressure equations derived. Next, we'll move on to the temperature equations and deriving those. And again, we start out with Raoult's law. So we're going to have y I p is equal to x I p I sat, and then instead of just having t there, this is going to be t bubble. Okay, and so since it's t bubble, we know our liquid mole fractions. So we're going to divide p over. We're going to be left with yi is equal to xi pi sat t bubble over p. We'll take the summation of it. I can draw it, probably not though. Yeah, I don't know. Summation, and then this is going to equal 1, like we talked about. The mole fractions are going to add up to 1, and then so we're left with 1 is equal to the summation of xi pi sat, and then we're going to have our t bubble, and then the thing is here, so we have 1 over here. So what's going to happen is we're going to multiply the p over, and then we're going to subtract it over and set it equal to 0. So we're going to have 0 right here, and we're going to have minus p. And I'll point out a little bit more that so we'll use this in our Python as kind of a way to, so you can see right here that we have our saturation pressure and our T bubble, and those are both two unknowns that we don't know, and that's kind of a big issue. That means we can't really solve the problem. So the only way to do this to get our T bubble is through iterations, and through iterations we're going to want to have this right hand side reach 0 at some point, and that will be our answer. So in order to do that, we sub in our P bubble right here, and we have xi P sat of our T bubble, or of our P bubble, or it's going to be P bubble of our T right here. And so theoretically, since this P right here is staying constant in our temperature equation, it will become our P bubble right here. So we can have P bubble substitute in over here as a function of our T and solve for our T right here to 0, and it will give us, and that should cancel out to 0, and the T that satisfies that is our temperature that we are looking for at our bubble point. So but this is the equation right here to use for our T bubble. So next we'll do our T do, and T do, we are going to use Raoult's law again. Raoult's law. We have YIP equals XI sat, and then T do. But this time we know our Y mole fractions because it's the dew point. So we divide P sat T do over. We get YIP over P I sat T do is equal to our XI. Take the summation again of it, because we know that this is going to equal 1. And then, so that equals 1. And we're left with YIP over P sat over T I T do is equal to 1. Okay, and then we'll use this again in our Python, and yeah, so this is our T do equation, T bubble, P do, pressure, dew point, and our pressure at bubble point. Those are the 4 equations, and that's how we derive them, and we'll use those in Python. Well, just one more thing to add is that we do have the same problem here with our PSAT and our TDO, with these both being unknowns. We're going to have to do iterations again, and we'll use Python to do that. Okay, we're going to be going over homework 1 part B, problem 2, where we obtain our bubble and dew points for temperature and pressure for a 40-60 molar mixture of benzene and toluene, and then we'll generate some VLE diagrams. Okay, so to start out with, we're going to use our props right here that we imported in to import our data for our benzene and toluene. So we'll name that as R equals props, and then we'll want an array, and then benzene, and then we want toluene. Okay, and then we can make sure that's right by doing R dot P VAP, and then like 350. Let's shift enter. Let's say R equals. Okay. It is R dot P that 250. Oh, I spelled. Okay, never mind. Okay, I see what we're doing. TOLUENE. There we go. And then shift enter. Yeah, so there's our array. So that would be the vapor pressure for benzene at 250 and the vapor pressure for toluene at 250. So we can move on from that and do our other known value, which is an array, or we'll do an array, and it is our concentrations, or our molar fractions, so 0.4 and 0.6. So shift enter. So we can now move on to defining our bubble pressure. Cannot spell right now. Bubble pressure, and then we want our liquid molar fractions and our pressure, or no, temperature, because of our saturation unknown. Okay, moving on, and we need, so I have our paper right here from where we define all of our equations. So this first one we need to do, we'll just call it S first, and then we'll do the X times our R dot P VAP of T, and then we'll do the sum equals, or wait, we'll do our PV, so our bubble pressure is equal to our NP dot sum of S. Then we hit shift enter, or not shift enter, we just hit enter, and then we want to return the BP, and we also want to return our liquid or our vapor fraction, and we do that by looking at Raoult's law, and we can see that we need to do our S divided by our PB or BP. Okay, now we can try this out. Bubble P, our X is our Z, and then our T would be our 350 according to our homework, and shift enter. See what this is saying. So oh, I need NP dot array. Yeah, okay. Well, I don't need help anymore. So NP dot array. That is 3. Okay. Shift enter, shift enter. Okay, so there's our answer right here. So we have our bubble pressure, and we have our mole fractions for our vapor. So the bubble P is good. So now we can move on to defining our dew pressure, and we want our Y and our T again. Enter. We need our colon. So looking at our sheet, we know we need our P dew is equal to our 1 over our summation of our Y fractions and our P saturated. So we can go ahead and do that. So we can go right here and do our how are we going to do this? dP is equal to 1 divided by NP dot sum of our Y divided by our R dot P VAP of T. Okay, and then we can return So yeah, we return our dP, and then we want to return the mole fractions for our liquid, which if we look at Raoult's law again, we can look and see that we need Y over P dew, Y times P dew over P saturated will give us our liquid mole fractions. So we need Y times our D P divided by our R dot P VAP T. Okay, try this out. So dew point Z and 350. Shift enter. I did a semicolon, colon, shift enter, and there we go. So we have our mole fractions, which look good. They add to 1, so that's good, and we have our pressure at the dew point. So next thing that we can move on and do is the temperature bubble point. So let's go ahead and define and do T or do T, and then we want our Y and P. Okay, so looking at our sheet, we see that Y, P, P sat, T dew equals 1, but we can simplify this down a little bit. So our P is staying constant here throughout our whole system. So we can make it so where we can use our dew temperature, pressure, minus our P, which is our system pressure, and we can use that function, that dew P function, and subtract it from the system pressure, and it should equal 0, because that dew point pressure should be equal to our system pressure at that temperature. So that's what we'll do, and that's what we'll use to we'll use a root function so that we can use iterations to get the temperature that we need closest to 0 with our initial guess. So sp dot optimize, and then dot root underscore scalar. Then we have lamb, and then T is what we want to get down, and then do P, there's capital P, and then we have our Y and T, and then we want an index of 0 here because we just want the vapor pressure, we don't want the mole fractions, and then subtracting our P, and that, like I was saying before, that's what we're doing, and then we have our initial guess, and we'll just say 315, and our method is Newton. And we want to return our T, and we'll have our Y times our P divided by our R dot P vap T. Okay, and then so we get that, like I was saying, from our Raoult's law. So that I've been talking about for the past, for our dew point, our dew pressure, and our bubble pressure, how we got our mole fractions. So we can go ahead and see if this works. So do T, Y, and P, or Z, and our pressure is, can't remember, 101,325. 101,325. So shift enter. What is this? Oh, I forgot the dot root. Okay, there we go. So yeah, we have our vapor pressure right here, or our temperature right here that our dew point is at, and then we have our mole fractions for our liquid. So the next thing that we can do is define our bubble temperature, and this will be X and T, and colon, and we're going to do the same thing that we did before, except this time we're going to be using our bubble pressure and subtracting it from our system pressure, and it should be equal to 0. So we do T equals SP dot optimize, and then we have dot root, dot root underscore scalar, then lambda equal, or no, T, and then yeah, so that's what, and return T, and then our we need our vapor mole fraction. So if we look at our paper, we can see that our liquid mole fractions are going to be our X mole fractions times our P saturated times our T bubble over our system pressure. So we have Y times P divided by R dot P vap and T. And shift enter. Wait, not shift enter. Let's see if this works. Bubble T. We have our Z, and we have our, this should be pressure. And we have our 101.325, and shift enter. Name Y is not defined. Wait. I typed in the one before. What was I thinking? Yeah. So, like I was saying, we need the liquid mole fractions and our P saturated, T bubble, and over P. So X. Oh, I guess we need some parentheses. So X times our R dot P vap of T, and then divided by our P. There we go. Okay, and our mole fractions make sense, and we have our bubble temperature at 368. So, okay. Next thing that we're going to move on to is a little bit of graphic. Okay, we're going to move on to starting to graph these and getting our data prepared for our graph. So to start out, we're going to do our we're going to need new x's for this, more so that the data is consistent and not sporadic, and we're going to create a for loop. So we're going to use these data, or these new ones to run the all the definitions farther in, so that we have data made for multiple concentrations, so that we can make a graph. So we'll have our x's concentrations, and we want np dot ln space, and we want this from 0 to 1, since that's like the max range that's like the range that we can have for our concentrations, and then we'll divide it by 21 times. Okay, and then our xs is going to look like this. So we have 0, 0.05, 0.1, 0.15, 0.2. So these are basically all of our concentrations right here that we're going to need, and these are what we're going to have values for our x concentrations. So we'll go ahead and define our T, which is 350, because this is what we're holding constant. So also the first thing that we're going to do is create the our pressure versus our XY mole fractions with temperature constant. So that's what we'll do. And so we're going to need open brackets right here for our new P's and our new Y concentrations. So we'll just do our Y's equals, because we're going to need somewhere to hold these values in when we start doing the for loop and calculating these new values. So we'll do our for loop. So for x in our np dot C underscore. So right now we're just gonna make a new array, and it's gonna be x1 or x's, and then we're gonna have 1 minus our x's, and that's basically, it's gonna cause our arrays to be basically inverse of each other, so that our x concentration is coming down as our y concentration is going up, so that it makes sense for basically how concentrations work, or how mole fractions work. So pull in there. So next thing that we want to do is we want to add in our bubble graph, or our bubble function. So we'll have, and we want to unpack it too. So we'll have P, because we have our pressure first in this array and how we returned it, and we have our gas mole fractions second. So this equals our bubble P xt has that, and then PS append P. So we want to append everything to this PS and YS. Problem, however, with this is that it doesn't keep it all in one single array. It has basically one number per each array that it appends to. So we have to, in order to fix that, we just do PS equals np dot r ps. Okay, there's that, and then enter, and then we have our ys equals npr ys. So that'll go ahead and return that. So let's just see what ys is. Model np has no attribute r. I need an underscore. What's going on here? See if it explains it. It's saying ys. Sure, I fixed it. I'm not sure what that changed there, but yeah. So I mean, that's basically what we wanted. We have an array with our pressures, and we have an array, or no, not our pressures. We have an array with our mole fractions. But the thing is, we want to index this to be our 0, because we want our more volatile component, which is our benzene. So we don't want this other one. So let's shift enter again. That's not what we wanted either. Not here. We don't want that here. Sorry, we want this here when we're appending it. Okay, now we're trying. Yeah, there we go. So now we have our benzene liquid or vapor mole fractions. So we can go ahead and try our PS. That's not gonna work. It's capital P. Yeah, so we have our bubble point pressures here too. So we can move on to start graphing this. So we can do fig equals make our subplots. And we want no rows. We'll just do fig make subplots, leave it open, and then fig dot add underscore scatter, and our x is going to be our liquid mole fractions, and then we want our y to equal our ps, and the name of this will equal our bubble and then we'll just do bubble line, and then we'll do mode equals lines. This is gonna be x equals ys. Yeah, we don't want that. Our ys, we want this to be our ps, and we want this to be our y1s or ys. So bubble line, and then this is going to be our dew point line. Okay, and then we have fig dash. Okay, yeah, so there's our benzene bubble line dew point. Okay, so we can make this look a little bit better. Fig dot update underscore layout width equals 800, height equals 600, and title equals F benzene and then we want at T equals, and we can use these, and that'll have whatever T we put up top be there, and then we want our K Kelvin, and then our x-axis is to be x, y, and our y-axis title x-axis title equals x-axis title equals okay, so yeah, that makes it look a little bit nicer. But yeah, that's our graph for our pressure versus XY at a constant T. And next we'll move on to graphing our temperature versus our XY at a constant pressure. Okay, so we'll move on to our what I just said. So basically we can just reuse this. We're just going to make some changes to it. So instead of our temperature being 350, our pressure is going to equal, what was it, 101,325. So 101,325, and then we'll still have our, well, we actually need our temperatures here, and then our y-axis are fine, our x1s are fine because we still want those concentrations there. Except here we don't want our pre-bubble, and instead we want our bubble T. And we want this to be X, that's fine, but we want this to be P right here. And then we'll do PS or TS dot append on the T, and then we'll keep that the same right there, and we'll change this to TS and TS. It's all doing the same stuff as before. YS, and then shift enter, and then we'll just check on these. TS, shift enter. There's our array at 350 constant, which is not what we want. 350 constant is not what we want right there. Okay, I figured it out. I had a P. I forgot to switch out a P for a T right here, but our TS's are looking fine now. So we can go ahead and draft this. I'll try and draft these both together down here. So just fig equals make underscore sub plots, and then we want rows equal 1, and then cols equal 2, and fig dot add scatter. We want x equal our x's, and then we want our we want our y to equal our ts, and then we want our name to be a bubble line. Name equals bubble line, and then we want our mode to equal lines. We want row equals 1, column equals 1, and then hold on a sec, I got we have our fig add scatter, we have our x's on our x axis and our t's on our y's, and this is our bubble line, and then the ladder next one, which is fig dot add underscore scatter. Then we want our x equals our y's, and then still on our y's we want our temperatures, and then we want name to equal our do line, and then mode is going to equal lines, and we want this on row 1 equals 1, column equals 1, and then we want to go with fig dot add scatter, add underscore scatter, and then we want our x mole concentration versus our y concentrations. So our x is going to be our liquid concentrations or mole fractions. So x's, and then our y is going to equal our y's. Okay, and then we have our name equals, we'll just call it our x versus y, and then we want mode to equal our lines, and then we want our row equal column 2. We don't want that. We want, well, so if I were to plot this fig dot show, that's Right, we need our 45-degree line on our x first y graph. So fig dot add underscore scatter. So x from 0 to 1, and then we want this be equal, and then we want y is equal to 1 to, or no, 0 to 1 still. Okay, and we want this to be a mode, or I guess, yeah, mode equals lines, and we want it on row equals 1, column equals 2. What did I do? Oh, I never ended though. Okay, yeah, so there is our temperature versus our XY line. I guess I can make that a little bit better too. So we'll just do copy and paste that, and then so we want this to be sure this can be P PA. That's yeah. Okay. So yeah, there is our temperature VLE graph with pressure at a constant. There is our x versus y, and there is our pressure versus xy with temperature at a constant. See if that's it. Yeah, so yep, we have our graphs for our VLEs for each one. And the code works. We accomplish this by defining our bubble points by first deriving them, and then figuring out that we can have our dew point minus our p equal to 0, and then we can use a root scalar function in Python and use iterations pretty much to find out our desired temperature, and we can use this to then model our VLEs. So yeah, that's it for the Python.